Intro. What do we know about black holes? It's a very dangerous object, an area of space-time with a gravitational pull so high that it absorbs everything in its vicinity, including light. For a long time, black holes have had a reputation of a space monster that consumes everything around it, and it can even destroy information. But how accurate are these accusations? What if we tell you that black holes can do more than destroy entire star systems? They can create them too. Let's take a closer look at their theories. Terminology. For starters, let's talk about the terminology. Are these objects actually holes? And are they actually black? If you ask scientists from different scientific backgrounds the question about the nature of black holes, their answers may be similar. But the approach would be different for a physicist, an astronomer, a mathematician, for example. That's because within a black hole, the laws of physics as we know them don't function the same way. And according to Einstein, gravitation within this object warps space so much that it forms a tear. So how does a black hole form? Can it form in place of any star? Scientists are still debating about the mechanisms behind the appearance of black holes. But the most popular theory is the gravitational collapse, which suggests that the hole can only form from stars, the mass of which is between 2.5 to 5.6 times larger than the Sun's mass. And yet, once the black hole is formed, it will only be a few dozen miles in diameter. Incidentally, the Sun ever became a black hole, its radius would only be 1.9 miles, whereas the original radius is around 432,450 miles. What is the significance of these numbers? What determines the compression limit at the point a star becomes a black hole? It's called the Schwarzschild radius, named after astronomer Carl Schwarzschild, who was the first one to discover this pattern. The thing is, any object in the universe can be turned into a black hole if it's compressed down to a certain radius. And the Sun would have to be compressed to 1.9 miles in radius. For Earth, that figure is 0.35 inches, just a little larger than a grain of rice or a ball in a ballpoint pen. You can use this formula and have fun calculating how much you'd need to compress the objects around you to make them into black holes. There are two main ways to interpret the way black holes form, one that is consistent with the general relativity theory, and one consistent with quantum mechanics. According to the general relativity theory, the entire surface of a black hole is a spherical boundary preventing light and matter from escaping. This is known as the event horizon, the point when the gravitational forces within the black hole begin to devour everything around it. It's a point of no return. If you cross the event horizon, you can no longer escape. If we somehow manage to get inside a black hole, we would discover that space-time is more warped the closer you are to the center, and at the very center, it would be infinitely warped. The scientists refer to that spot as the gravitational singularity. Here the concepts of space and time no longer have meaning, and all known laws of physics no longer apply. Of course, a black hole doesn't actually have a surface as such. An event horizon is just a boundary where the black hole starts. Technically, you can't even call a black hole an object in a geometrical sense, because it doesn't have a permanent shape or surface. You cannot feel or touch the event horizon. The easiest analogy is this: imagine a being in a completely dark room. You stumble upon a door leading to an exactly the same room. In this case, the door is a real object in a specific location. It would be a different matter entirely if walking around in a dark room, you stumbled into a black hole. You would simply not notice the transition. There's no solid physical boundary in front of a black hole. A black hole is a place where the mass has warped space-time, and as a result, no object can leave it. Once it crosses the boundary, Everything that entered the black hole will forever remain beyond the horizon. Inside a black hole, thesis, one of the fundamental questions occupying the minds of astronomers around the world. What's inside? What would an observer experience inside the black hole? And what would that look like to the outside observers? In the moment when you cross the event horizon, the reality would split into two parts. In one, you'd instantly evaporate from reality. In the other, you'd be frozen in place, safe and sound, before gradually disappearing forever. As we already mentioned, crossing the event horizon would happen completely unbeknownst to you. Think back to the dark room analogy. What's amazing is that as you move closer and closer towards the gravitational singularity, you won't experience any turbulence, any pull, or pressure. You'll simply be in a state of free fall. And if we're talking about your subjective perception, there will not be a horizon for you. We must say that this theory only applies to large-scale black holes, millions of times larger than the Sun. Whereas, in the case of smaller black holes, you would experience a deathly discomfort. The gravitation would affect your body disproportionately, and you'd be stretched out like a strand of spaghetti. And by the way, that's the official scientific term for this process, spaghettification. But for the purpose of this experiment, let's imagine we found ourselves inside a fairly large black hole. We are doomed, but at the very least, we won't die instantly, making a relatively steady descent towards the singularity. So, you're calmly flying through the infinitely warped space, headed for the gravitational singularity, while the outside observers claim that you have vanished next to the black hole. Who's right in this case, according to physics? Both. Additionally, according to Stephen Hawking's theory, you can slowly vanish within the black hole, be essentially erased from the universe, which leads to a serious paradox, the black hole information paradox. In accordance with the laws of quantum physics, from the point of view of the observer, you cannot cross the event horizon. You must stay outside of the black hole. One of the fundamental laws of physics says that information cannot be destroyed. When you are inside the black hole, the physical youth atoms your body is composed of cease to exist. From the observer's point of view, this would go against the law of physics. Stephen Hawking determined that, aside from everything else, black holes also evaporate on the border of the event horizon. So-called virtual particles are formed, although the probability is low. One particle can be devoured by the black hole while another remains outside of it, turning into radiation Hawking radiation. This way, black hole can very slowly lose its mass. It would take 10 to the power of 100 years for a supermassive black hole, which is formed through the merging of several black holes, to evaporate. And in theory, any object that enters a black hole stops existing as we know it. All of its matter turns into heat, which goes against the principle of indestructible information. That's something known as the black hole information paradox. Fortunately, the scientists succeeded in getting closer to unraveling this paradox, but not without some caveats. According to research by students from the University of Ohio, black holes are actually gigantic fuzzy balls, or as they are literally christened in the study, fuzzballs. Contemporary theory suggests that a non-spinning, non-charged black hole is characterized by a single indicator-its mass. If an object enters the black hole, all of its characteristics and state at the time of the event will make no difference. All that will change as a result of this absorption is a mass increase. There is an expression to describe this aspect: black holes have no hair. It's trying to say is that all non-spinning and non-charging black holes of the same mass, even if the information about the object is stored inside the black hole, it has no influence on its radiation. But string theory physicists found an elegant solution for this paradox. According to this theory, all matter surrounding us is made up of thin vibrating quantum strings. To understand the way they work, we should imagine the strings of musical instruments. Normal strings can vibrate, bend, fold. The same thing can happen to these quantum strings. And so, according to theoretical physicists, A black hole may look like a fuzz ball, created entirely from quantum strings vibrating in accordance with their special quantum laws. In this case, we can imagine a black hole not as a place full of densely packed particles, but as a yarn ball of quantum strings. In this theory, there's no singularity or even an inside of the hole. Space-time simply doesn't exist beyond the event horizon. Consequently, you, as the object, couldn't enter the black hole. Your fall would change the vibrations of the fuzzball, which would affect the radiation emitted by the black hole. As a result, the information is not destroyed. The fuzzball theory helped to resolve another paradox pertaining to the physics of black holes. We already mentioned Hawking radiation, but we didn't specify that the mechanism of this hypothetical radiation emanating from the black hole is linked to creating virtual particles in a vacuum. Generally, these particles can be observed in the same way we see light radiated by the sun and other high-temperature bodies. The difference between Hawking radiation and electromagnetic radiation from celestial bodies, such as stars, is that in the case of the latter, photons are generated from interacting elementary particles, as opposed to from nothing. Photons emitted throughout the lifespan of a black hole will have an entropy too great for the process to correspond to the general principles of quantum mechanics. In a nutshell, entropy is a measure of how evenly the energy is distributed within the universe. The principles of quantum mechanics require the photon entropy to be lower than the entropy of the black hole. To resolve this paradox, scientists considered a phenomenon known as the wormhole paradigm. To properly calculate entropy, you must account for the photons leaving the gravitational field of the black hole, as well as the particles that enter the black hole. If we view a black hole as a classic general relativity object with an event horizon and a singularity, the equations have inconsistencies. However, black holes are viewed as the string theory fuzzballs. That problem is solved. And very recently, in January 2022, old man Hubble delivered another surprise related to black holes. Turns out, the radiation we discussed can directly influence the process of forming stars, lighting up the stars in a faraway region of space, as if in confirmation of the fuzzball theory. While observing the faraway galaxy Hines 210, Hubble discovered a flow of radiation moving towards a dense gas cocoon from somewhere around the center of the galaxy, presumably where a black hole must be. Spectroscopy showed that the radiation moved at the speed of around 1 million miles per hour, crashing into the dense gas formation and changing its density. This is opposite to the effect observed in larger galaxies. There, matter approaching a black hole is swept up by the surrounding magnetic fields, creating a flaming burst of plasma. These jets move at a speed close to the speed of light. Any gas clouds that get in the way of these jets emitted by a black hole would be too hot, limiting their ability to cool down and form a star. The matter will simply be unable to condense into a star. With the less massive black hole at the center of Hines 2-10, and the softer radiation it emits, gas was compressed just enough to start the process of forming a star. Hines 2-10 is only 30 million light-years away, close enough for the Hubble telescope to record images and spectroscopic evidence of black hole radiation. Scientists expect that in the future, even more research will be dedicated to studying black holes in such dwarf galaxies. This could become a key to uncovering the mystery of the origins of supermassive black holes in the early universe. The main clue may have something to do with the mass of a galaxy and a black hole at its center. This type of research once again brings up the undeservedly tarnished reputation of black holes. Turns out, as well as consuming, they can also create. And this is yet another reason to take a fresh look at black holes, not as some scary monsters hiding in the depths of space, but as incredible, unique objects that turn our understanding of space upside down.